Okay, science time. We're talking today about magnets, or talking a little bit about magnets. Your bell work asks you to explain, in terms of your laboratory, explain magnetic domains. And we're talking about magnets. Magnetic forces. And the objective, what does the objective say, Aiden Streety?
Diagram the causes and effects of magnetism.
There we go. Diagram the causes and effects of magnetism. Let's write that down. Diagram the causes and effects of magnetism. You remember the four fundamental forces of the universe? We talked about these a while ago. Let's remember them. Four fundamental forces of the what? Universe. The whole show. There are only four fundamental forces in the entire universe. What are they? Strong nuclear force.
Electromagnetic force.
Not Streety. Electromagnetic force.
Small nuclear.
You're on the right track, but that's not the right word.
Weak nuclear force.
Weak nuclear force.
And then gravity.
And then our old boy, gravity. Remember, these are in descending order as we go down the list. The strength of them does what? Goes down. These are weakening forces. I mean, the forces themselves aren't weakening, but as we go down this list, the forces are weaker. This one is stronger than this one, is stronger than this one, is stronger than this one. This is the weakest. But as we go up the list, they get what? Shorter in range. The gravity has the longest range. It's the weakest but the longest range. The strong nuclear force is the strongest but has the shortest range. Now today we're talking about this one, electromagnetic force. What two forces that we're somewhat familiar with probably make up the electromagnetic force? Magnetism and electricity. So we're going to talk about both magnetism and electricity this year, but for now we're focusing mostly on magnetism, which is part of the electromagnetic force. The electromagnetic force. We'll talk more about the electromagnetic force when we talk about waves, and then when you're in physical science, we'll talk more about electricity itself and things like voltage and current. But for now, we're talking about magnetism. And I have here, I have some magnets. Let's take a look at a couple of magnets here. I'm going to need to have this out of the way a little bit better. This is a magnet. This is a magnet. How do you know?
It's magnetic.
Maybe you can't see that very well, and certainly the camera can't see that very well. Check this out. Let's go back to our old boy, the marker. Where's the marker? That marker that I've been using for the last month for every single demonstration is dead. So this is a new one. Sorry, fans of the old marker. We got a new marker in town. So I'm going to draw two things this time. Wow, this new marker has this kind of shape a little bit. Yeah, bad, ugly marker. This boy never going to fill the shoes of the old one. And then we also have, I'm going to draw this, I have orange. Go Rams. I have this paddle-looking thing here, what looks like a paddle. And it looks like that. There we go. Okay, so I have these two. We're going to say they're equal in mass. That's not true, but they should fall at the same rate. Remember Newton's laws that say that even though this object is heavier, it is significantly heavier, that a lot of times people think it'll fall faster, but actually they should fall at the same rate. I hope they don't break, and I hope they don't break the floor. I should be more careful and put something on it.
It probably won't fall.
Is your Chromebook in here?
No.
Okay, good. Okay, so here we have Mason's purse. I'm going to drop these both, and we're going to see which one falls. We're going to see which one falls faster. This is an old demonstration that we've done before. Which one should fall faster? No, be careful. Say it again, Aiden. Neither of them. They should fall the same rate. Yeah, they did. They both land at the same time, even though they have different masses, because the one with the smaller force also has a smaller mass, and therefore the acceleration evens out. The one with the larger mass has the larger force, so they end up with the same acceleration. That's not the point. What I'm going to show you is that when we drop them nearer the board, Watch what happens with the forces on this. Watch what happens with the acceleration when I drop them near the board. Did you see that? So this one, the marker, only had really one force acting on it once I dropped it. What was that one force acting on it? The force of gravity. But the orange boy, something else was going on here. We had the force of gravity. It's a larger force of gravity. Why would I draw this angle longer? Or sorry, this arrow longer? It has more mass and therefore more weight, so the force of gravity acts on it more strongly. But also, if we pretend this is the whiteboard here, it had another force acting on it because it was so near the whiteboard. What was that force?
Magnetism.
Which that one is not quite as good a demonstration. But it also has the magnetic force pulling it this way. F sub m, the magnetic force, was pulling it that way. And so its motion ended up being kind of a combination average of these two, and it ended up going like this, and eventually it collided with the whiteboard, and then friction was acting on it too, and it started to slide down it, right? So it had an extra force acting on it. We know it had an extra force acting on it because it did what? What is our direct evidence that it had another force besides what the marker had acting on it? Yeah, it accelerated. Whereas the marker just fell straight down, the magnet does not fall straight down. It instead falls at an angle like this. So we know there must be another force acting on it because we know that it's accelerating. Remember, any change in motion is caused by an unbalanced force. And so since this is changing its motion, it must have an unbalanced force, and that force is provided by what's unbalancing the force to make it pull towards the board? Magnetism, one of the fundamental forces of the universe. So really, this one, in a way, both of these have all of these forces. But in a macro scale visible way, this one is affected by two of the fundamental forces that we can see. We can see it's affected by gravity. We can see it's affected by the electromagnetic force. Why? Why? That's the big old dang, that's science. This question here is science. That's our investigation question. Why does this one have an extra force acting on it that this one doesn't have? That's the question. That's what we're going to answer today, or we're going to try to answer today. It also tells us something about the whiteboard, doesn't it? Because if I do the same thing, but instead of the whiteboard, I have this meter stick here. I was worried my hands were going to get chopped off, but why is it not attracted to the whiteboard or to the meter stick? Yeah, the meter stick has something else going on with it that the whiteboard didn't have. Just in the same way that the magnet has something going on with it that the dry erase marker didn't have. And furthermore, if I drop this magnet here, the whiteboard is still behind it. So why did it still not pull towards the whiteboard? Why if I drop it out here does it not pull right to the whiteboard? You see, there's a couple different questions here. Why? First of all, let's answer this question. Why is it magnetic at all? What is going on inside of it that makes it a magnet? What makes magnetism? That's our first question. What makes magnetism? What makes an object magnetic where another one isn't? And it has to do with, do you guys know about atoms at all? Which of the subatomic particles, protons, neutrons, and electrons, which one do you think this probably has to do with? Is this just going to be a guess for you? Yeah, it does have to do with electrons. It has to do with electrons because the electrons are the physical manifestation of the electromagnetic force in the universe. It has to do with the electrons. So we can think about, I'm going to draw a black box here and an orange box here. The black box is going to represent my black dry erase marker, and the orange box is going to represent my orange magnet. Okay? You with me so far? Both the black box, the dry erase marker, and the orange box, the magnet, are made up of atoms, as you know, which are made up of subatomic particles, which you know. And in this one, let's say there are all these different little atoms are floating around in here. Well, they're not floating around. They're bonded together in here. And similarly, this one. Now I tried to draw the orange one a little bit neater because it probably has a little bit more of a what we call a crystal lattice. They're arranged in more of a pattern. But each little atom has electrons that are buzzing around. So I've drawn kind of big dots to be the nuclei of atoms and the little dots to be the electrons of atoms, okay? Kind of randomly arranged. This is a gross oversimplification, but in this orange one, in the magnet, the atoms or the electrons, we can say, are all generally, roughly, hanging out on the same side as of the atom as the other one. So we get a net, not quite movement, but a net direction of electromagnetic force of this way. So in this one, it's randomized. There's no net direction of electromagnetic force. But in this one, the electrons are arranged in each atom pointing a certain direction. We call that a magnetic domain. This is what your bell work was about. The bell work said, explain magnetic domains. Well, what's a magnetic domain? Yeah, it's a region within a magnet that has a certain magnetic field. That exerts a certain magnetic force in a certain direction. So this magnet is made up of, these are going to be very, very rough, and I'm not like looking at it or anything. I'm making this up. But we can say this magnet has these different regions, right? Domains, regions on it, and each one of these has a general magnetic force acting on it. We'll say some of them are that way, some of them are that way, but on average, they all on average point the same way. So the magnetic domain has several different magnetic domains, the magnet does. And some of them point that way maybe, this way, this one a little bit cockeyed, that one points like that, this one. They're all roughly, like on average, they're all roughly pointing, we'll say up. And we'll call that end of the magnet north and this end south. Every magnet, boys, every magnet has, I'm going to fill in a number here, how many poles? Every magnet has 2 poles. What if, and I hope since this drawing of magnetic domains is so good, I hope you understand, what if I cut this magnet in half?
It will
Swoop!
also still have
one because it really doesn't.
I cut the magnet in half, and now, but it's not like I cut the south pole off, because each domain still has a north and a south pole. Every one of these domains still has a north and a south pole. They don't necessarily all line up, but every one has a north and a south pole. Just like if I cut this one in half, call this north and this south, just like if I cut this one in half, there's still atoms here, and the atoms still have most of their electrons on this side, and so there's still a magnetic domain. Every magnet always has 2 poles. Just like every cat, just like every cat, this is a good drawing of a cat, do not at me. Every cat has a front and a back. What if Crazy Joe Vogel comes along, Crazy Joe Vogel, maybe, Crazy Joe Lambert is what I meant to say. Crazy Joe Lambert comes along with his scissors and cuts the hat in half. And now we've got 2 halves. I didn't mean to invoke the name of Joe Vogel, I'm sorry. I meant Joe Lambert, who is crazy and probably has chopped cats up before. Now we have 2 halves of a cat. But guess what? Just like this still has a front and a back, and this still has a front and a back. So it's fine. So no. But you see what I mean? Like it's the north and south poles of a magnet are conceptual arrangements like front and back. Like heads and tails. If I have this coin here with it, which is heads and tails, right? If I cut it in half very, very thinly, it'll still have a front and a back, right? Each part of it, it's not like I have only tails on this one and only heads on this one. They both will have both sides of a magnet. Maybe that's not a great example because the print will still only be heads on one and there will be nothing on the other side. But each coin, each of my half coins, will still have a front and a back, right? Speaking of my coin, what's the coin made out of? Generally. Metal. This is a magnet. How come? Uh-oh. The magnet is broken. Is it? No. Here's another piece of metal. Here's another piece of metal. Come here, little other piece of metal. Here's another piece of metal. The magnet is not broken. So what's going on with the quarter? The quarter is broken?
No, the quarter's not made out of magnetic.
The quarter is made out of metal, but not all metals are magnetic. There are different kinds of magnetism. We have what are called ferro magnetic materials. I think that's the word your book uses. Let me make sure that's right. Because on previous videos I have used the wrong vocab word for this. Is it? Is that not in lesson 1? No. I think you do recognize the word ferromagnetic. Is that right? Okay. We'll just. Shh. Well, we'll say it's ferromagnetic. This is what is sometimes called a permanent magnet, but this is a substance, usually iron, but it can also be nickel or cadmium, or these are rare earth metals that are made out of neodymium, which is a metal on the periodic table. But what? No, not usually. I'm sure it does have radioactive isotopes, but neodymium is another metal on the periodic table. But several of the metals exhibit this property of ferromagnetism, which we sometimes call a permanent magnet, but where their domains are aligned, more or less. And actually, what determines whether a magnet is strong or weak, what we might say weak, let's say this is going to be really hard to see on the screen probably, but how am I going to do this? I have my paperclip in my hand. And if I move the orange magnet over it, we can see I have to get to about there before it picks the magnet up. Now if I use my quite strong magnets in a jar, I can't see what's going on. Wait, what? Even closer. No, this should be a stronger magnet. But the strength of a magnet, let's use this one. The strength of a magnet is determined by, there we go, by how much the domains align with each other. The degree to which the domains line up is what determines the strength of a magnet. So if the domains are aligned, if they're all aligned, it will be, I guess, an infinitely strong magnet, but there's always going to be some fluctuations between these. There's always going to be some randomization with the electrons and the way they're lined up. In a paramagnetic material, is that another word you recognize? No. Paramagnetic material will align to a magnetic field. They will align to a magnetic field. So that would be like this paperclip is paramagnetic. It itself, let me get 2 paper clips. Well, I'm going to get the paper clips out of the drawer of magnets, and so maybe they have been magnetized. But the paper clips themselves are not. They don't attract each other, right? Bloop, 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 bloop. Nope, no attraction. They don't attract each other. They don't exert a magnetic field, but they will align to a magnetic field because they are paramagnetic. Yeah. So this is ferromagnetic. It exerts a magnetic field. These are paramagnetic. They respond to a magnetic field, but they don't themselves exert a magnetic field. And then the other kind of material is, I kind of ran out of room. I'll put it over here. Dimagnetic. Well, let's make the letter M much better than that. Dimagnetic. And these, I'm going to put generally, no interaction magnetically. Now, depending on if there's a magnetic field of enormous strength, they will sometimes, the electrons, because basically the electrons are randomly arranged in a diamagnetic material, like the marker or like the meter stick are diamagnetic. The electrons are randomly arranged and they stay randomly arranged and they don't even line themselves up if there's a magnetic field nearby. Except if the magnetic field is extremely strong, maybe they will. But even this fairly strong magnet that I have, obviously, no interaction with the meter stick, right? It's wood. The electrons are fairly randomly arranged and they don't align themselves to a magnetic field. It has been shown, a really neat example that you can look up on your own. I don't ever link things in the description, but if I were, I would do this. There's a study done where they had a supercooled rare earth magnet, a very, very strong magnetic field, and they levitated a living frog. The frog was a live frog, normally diamagnetic, just like half of a cat. Normally does not interact with the magnetic field at all, but then this extremely strong magnetic field, the frog was levitated in it, which is pretty cool. Now, that's not very common. That would have to be an extremely, really, really strong ferromagnet, or we might even, probably have to be an electromagnet, which is a different word. Let's write that one above it. An electromagnet is an object that exerts a magnetic force when a current is applied. And this is so many of the things that we're used to using technologically and contain electromagnets. It's how speakers work. It's how at least it used to be how like screens, like plasma screen televisions and computer monitors worked. It's how solenoids and alternators in cars work. But they exert a magnetic force when a current is applied, and that's really handy. You imagine, I know someone was picking up. You did your magnet fishing, right? You did your magnet fishing, and you went around. You picked up all the iron filings and the paper clips and stuff, and then you had to like scrape it off so the next guy could go. But if you had an electromagnet, you just turn it off, and all that stuff falls down because of gravity. And then when you turn it back on again, it'll pick it up again. So that's how an electromagnet works. And in fact, every time an electric current is applied to anything, it exerts a magnetic field. There's an idea called the right-hand rule, where if the current is applying, you use your right hand. If the current's going this direction of your thumb, there's always going to be a magnetic field in the direction of your fingers going around it. The way we make an electromagnet is we wrap a wire that's carrying a current several times around a rod. I think I might even have one in here, an example of this. Yeah, the screwdriver. This would be probably fairly weak, but an example of an electromagnet. So the wire that carries the current, every little turn of this wire is going to have a magnetic field going this direction around it, which will give us a net magnetic field of north to south in this direction. Now, the last thing I want to talk about magnets, we talked about magnetic domains, and I have here, this I think is such a cool, I don't even think this is, I know it's not in your explorations actually. I'm going to angle the camera down over here so you can see what's going on. This is called, I think it's magnetic induction. It's used as magnetic braking, but this is a piece of copper, which is a different kind of magnetic. We had ferromagnetic, where the domains are aligned and they exert a magnetic field force. Paramagnetic, where they will respond to a magnetic field force. Diamagnetic, that responds not to a magnetic field force. And then electromagnetic. But there's this other one, which is copper, which doesn't itself exert a magnetic force, and it doesn't align to a magnetic force, but it does impede movement in a magnetic force. So if I have, let me show you this. I'm going to angle these two things at both the same way. I have this, slide them on down. Right, that's just like that's how things slide down a ramp. But if I do the same thing with this copper, isn't that sick? I think that is the sickest thing. Let me show you with something that isn't magnetic, so you know it's not the copper being sticky. This is a little compass that's not magnetic. Isn't that sick? So it impedes a magnetic field. Well, it slides because it's at an angle, right? It just slides because the normal force works up in this direction and the gravity works down, so together they pull it that way. But because it impedes the magnetic field, even if you drop it in slow-mo, I don't have slow-mo, but if you drop it in slow-mo, or the way we usually do it is swing it on a pendulum, you can see it in slow-mo, slowing down to almost a stop right here before it finally collides. What was your question, Aiden? Why? Yeah. So basically, as the magnet, which exerts a magnetic field, moves over the copper, it creates eddy currents in the electrons. It makes the electrons spin to align with the magnetic field, but it doesn't align the entire domain to the magnetic field. And that spinning of the electrons removes energy from the system in the same way that friction would remove the energy from the system. So it makes it basically, this acts as if there's a lot more friction than there actually is. because of the eddy currents that are created in the electrons in the copper. I'm going to show you a video when we're done. I'm going to show you a professional video made by real human beings when we're done filming this little video of someone they have a huge copper plate and they swing a very strong magnet and it doesn't clap. It just instantly freezes there, and it's pretty sick. In very high end like semi-truck brakes, they use this instead of, like, the normal way to make brakes is you just basically squeeze something as the tire is spinning, and that thing makes the tire stop. And in magnetic braking, they use a very strong magnet and a pretty thick piece of copper. And this is the nice thing about this is that in actual friction brakes, eventually the brake pad wears away. In this, since you're only generating magnetic eddy currents, there's nothing that wears away. They don't even touch. They just slow down through this magnetic eddying force. I'm going to pass both these around. Be really careful with this. Don't let this get near your Chromebook. It will ruin it. Don't let it get by your Apple Watch or your phone or anything that has any kind of electronics in it. But I want to pass around this copper and this, and I want you to just rub it over. It's pretty sick. It feels really cool. It feels like you're moving it through honey or something. There you go. It'll ruin a magnetic or a electromagnetic device like a phone or a watch or anything. Does anyone have any questions? I'm going to try to get this camera back to where she belongs.
These Chromebooks die in the slightest magnetic field.
Mason bricked our computers with a.
Isaiah had a headphones that connect with magnets, like close with magnets. I put it near the Chromebooks, like right here, turn it off for a second.
That's great. Nice.
Bricked all of our computers in the middle.
Do you have questions about magnets besides your anecdotes, which I'm happy to hear about? But do you have questions about any of this? How many poles does a magnet have? Always 2, no matter how many times you cut it.
5.
No, 2.
5.
Bye.